Thank you. I'm going to speak on boundary value problems in function theory, so higher dimensional problems, and try to fit that in the part of the pseudo symbols for pseudo discrete operators. This is the layout of my talk. Sorry, but with the screen, my buttons are a little bit slow on React. This is the layout of my talk, and I'm going directly to the part. Has been considered several times in here, possible generalization of complex analysis to higher dimensions. And you are interested in doing that because you are looking problems, for instance, in three-dimensional space, and you want to modulate in that, and complex is nice to fatiate the results, but not to give a global analysis. Most the classic approaches are done by combinatory graphics, but they work very fine in complex analysis, but in the moment you go higher dimensional, you kind of lose the geometry. And this is due to the fact that Laplace-Beltrami operator only coincide with the classic Laplacian when the dimension is exactly 2. So the ideas they have is to either use finite type differences, so to fit the function to the geometry of the problem, or also discrete differential geometry, but this is something that it has to be, to some extent, you have the operators who fit the function to the graph, and so you change the graph and you change the functions. So it lacks a kind of a common potential theory for these kind of situations. And the first approach, at least in Clifford analysis, is started on the 60s, 70s with works of Krupek and Sprosik, which are based in the discrete star Laplacian, which is simply evaluating the function at one point and then compensating all the entrants by all different directions in the lattice in the kind of a Kirchhoff law of electricity. Now, the problem you have here is that this is a scalar operator, and you have to construct still the Dirac operator, a kind of factorization that is an analog of the gradient operator. So for that factorization, well, the main problem with the discretization is that you don't have anymore the limit case. So you only have the backwards and forward differences. The forward where you compare the value in the point with the value immediately after or immediately before in the case of backwards. There is a second one that I'm not referring here, which are the centralized differences, which is simply comparing at each point. You ignore the value on the point, but you compare the backward with the forward element and divide by 2h. But for that, you have to be careful because that requires a lattice twice the size. And if you are not careful with the fundamental solution that you choose, you risk to introduce afterward aliasing problems. But that is for the practical effect. So these are the derivatives that you have. They apply very well for the star Laplacian, but it lacks the replication of the classic derivatives in the complex plane. And for obtaining a kind of decomposition of this kind, you simply split each of these direction vectors into two basis elements which are going to replicate the orthogonal directions of z and z parts. So they are more or less orthogonal to the, orthogonal to each other, but corresponding to 45 degrees with respect to Ej. So the sum of these elements is Ej, but these elements have additional properties, and those additional properties are the ones that we are interested. First of all, they act as projectors on a certain space. They kill each other they are zero divisors. But when you operate these elements, Ej plus with E minus plus E minus Ej, then you get back -1. So you recover the unity element. So this allows to decompose the star Laplacian as a product of backwards and forward differences. These actually can commute. I use forward, backward, but you can put backward, forward in each direction. And you can also choose by which order these elements appear. So you have a discrete Dirac operator and you have the adjoint Dirac operator. So you put in the E plus direction the forward derivative and E minus the back derivative, or vice versa. Since E plus J square is 0, that means that each time I multiply by E plus, I annihilate this term. So they act also as a kind of projector. So for practical purposes, you need the small LP spaces, which the relevant is the obvious part that if your domain is bounded, then in the moment the function is in one small LP space, it will be in all of them. And you also require an adequate discrete Fourier transform, which pick one such sequence of elements. I'm going to consider the function defined in whole lattice, Zn, and creates a function with compact support in this cube of L2. And this function, well, you can put it, define it as a torus, but I prefer to give 0 outside this cube. So the function is defined by the sum of the inverse discrete transform average to the space dimension of the lattice. And face this discrete Fourier transform, so you have that the inverse is simply calculate the Fourier transform of your function that you obtain and restrict it back to the lattice. So this goes relatively fairly, nothing more to say. You need also a corresponding of a discrete fundamental solution, which is simply the delta Dirac, that's Portuguese, delta Dirac, which reconstructs simply 0 everywhere and has singularity of dimension of the space in the point 0. And you define discrete fundamental solutions as the ones that the operator acts on the left and obtain the delta discrete Dirac function. So the symbol of the discrete Laplacian, discrete star Laplacian is well known, d square, given here. And you can, since the Dirac operator is obtained in terms of translations +1, -1 of the function, then its symbol is obtained by 1 minus modulations of that element. And that goes rather straightforward. So this means that the fundamental solution for the for the discrete Dirac operator that I have here is nothing but calculating the Fourier transform of his discrete symbol divided by d square and restricted to the lattice, which gives an ugly form, but you can work with it. The properties, simple, when the lattice mesh goes to 0, This symbol is going to coincide with the standard symbol of the Dirac operator. And the Fourier transform of this symbol, discrete symbol, it's going to have a very nice decay of the order of n-1. And this ensures that the discrete fundamental solution is now in LP space for p larger than n divided by n-1. So another result is the error estimate between the discrete fundamental solution and the continuous one, that at each point is evaluated by the mesh side, and then the dimension, the value of the point, power n. That is, well, you can control the error with the mesh side, but you still have some problems. And of course, the results you get for the discrete Dirac operator, you have similar for its adjoint. So when you use these formulas to the discrete Stokes formulas, then something nice appears. Your basic potential theory in the continuous case lives of one layer and two layer potential integrals. But whenever you use the discrete Stokes formula, then what you have is that you always need to have the values in two layers, one at the boundary and one immediately inside the domain. So you have, for the upper half plane, the 0 and the 1 layer are the ones that you need to describe the Cauchy formula. And so if the function is monogenic in the discrete sense, so if this operator is 0, then you retrieve the Cauchy formula, the upper Cauchy transform, which depends on the values of the function that you assign in the 0 and 1, nothing else. So with this, now I have, before passing to the other, it's better to say something. When you calculate the discrete fundamental solution, you can do it by two ways. Either you go directly, develop it in terms of series, and you go calculate it, which is prone to obtain errors because you are working with series, you have to make approximations and on and on. Or you do a clever thing and you simply go to the frequency space to the Fourier domain. And if you go to the Fourier domain, you also observe another thing. You also have here E plus, E minus, so that also indicates that you're going to decompose your function into n-1 variables and then splitting the last part, the combination of E plus 1, into the algebra generated by these two elements. So 1, E plus E minus, and the product E plus E minus. This gives 4 terms in the Fourier domain with values in the algebra n of dimension n-1. So when you calculate now in the Fourier domain, you have to always apply the n-1 dimensional Fourier transform, but you get now that you can construct for the boundary value of discrete monogenic functions, you have now a nice description for what should be the Hilbert transform in the discrete, in the Fourier domain. So the Hilbert transform, you need to pull back this nice symbol and you obtain the upper and lower discrete Hilbert transform. They satisfy the properties, and even better, I'm doing this here for the upper half plane, but you can do it for any dimensions because you already know that Hilbert transform, his components in each direction are the Riesz transforms, and you can construct them with respect to any of the axes, and you even transform it, Riesz transform, adapted to any curve that you have in the space, where you need only to pull this mapping for the real line that you have. So the nice properties is that now that you have the Hilbert transform, you can define the Hardy projectors, the Hardy space projectors, P and Q, and you have something funny when you compare the cases of the upper half plane with the lower half plane. These operators, the projector in the Hardy space, where it's corresponding to the projector on the Hardy space, well, in the 1 minus the Hilbert transform, these two, when the mesh side goes to 0, these two glue together, while these two glue together. And you can now define what is a function in the Hardy space, simply implying that the Hardy projector leaves the function invariant. Now, I have here some examples, toy models of applications on this. So one thing you have to keep in mind is that if the function is discrete monogenic, the layer, the value that it has in one layer has to be connected with the value of the function in the 0 layer. So it's enough to give one of these to construct the value that his monogenic analogous must have in the 0 layer. And from here, that's what this operator, the generator of the pairs of 0 layer, 1 layer that construct a discrete monogenic in the upper half space. And then you apply the Cauchy operator and obtain solution. This is rather nice. And well, that's the idea of the proof, but let's go ahead. You have also a jump problem, and that jump problem has a nice condition because you have here a projectors. You need to have a very specific kind of jump where instead of having the value in the upper part and the value in the lower half plane, you don't need all of that jump. You only need the projection on the E minus and E plus. If you have this difference, then you can solve the problem because you simply generate the monogenic part with the G plus, the solution that comes from this element. You decompose this in twice, in the projection in E plus and E minus. G plus you extend as usual. G minus you extend to the lower part, and this gives you your solution in the jump, which will be a monogenic function with the exception of the 0 layer, obviously. The convergence results, well, the convergence results tell us what we already know. It's not enough to have a function in the big LP space. You need to have some kind of Holder continuity. But if you have a function in this space, then you can estimate the restriction, the norm of the restriction to the lattice to be in a small LP plus n minus 1 divided by alpha. And with this, then you can obtain an estimate between the continuous Cauchy transform and the discrete one. In order to obtain this estimate, you have also to have some measure of control on the derivatives of the continuous function. It's not enough that they are in the Hardy space, and older, you need to have some measure of control on these first derivatives. And the estimate error will always be of degree h. There is one term here which says that no matter what you do, the convergence is always on the size of is only depending on the mesh size h. So now let me jump, and that I'm going to jump relatively fast because that's what you have, where the pseudo-differential operator theory applies here. This is the standard, so I pass over. What interests me is that cases already was studied cases of difference operators apply to the torus. So when the frequency is based in a lattice, when you obtain the frequency in a lattice, you can define the difference operator, and you have already a theory for pseudo-differential operators on this case from Agranovich and Hujansky, Turunen, and Wirth. So, of course, we are always interested in the class of 1, 0, but you can simply estimate the difference operators, powers of the difference operators, and powers of the derivative in the space by a certain decay of the function in the lattice. Now, in a nice paper in the archive in 2017, but which has been recently published, there was an idea of constructing discrete symbols when your space is a lattice and the frequency is in the torus. So you can define the operator in the standard way. You have to use the discrete Schwarz space in terms of semi-norms given here, and you use the space of temporal distribution that is topological dual. But if you do that, you have now a problem when you try to construct the symbol, because demanding that the symbol is smooth whenever you are in this, you fix the space variable, it's okay. But when you have to control the decay of the derivatives and the differences applied to the symbol, you cannot impose anymore a decay because you are in the torus and there is no decay at infinity. So you have to, and that was really a nice idea, to make the decay in the lattice variable. If you do that, then the theory goes practically fine, but you control the decay in the space variable, no longer in the frequency one. Now, these were the ideas that I was trying to carry to the Clifford value operators. And here I have to point out some problems that you have, because although some things go straightforward, most of them are not. What does not go straightforward, for instance, is the inner product. The standard inner product that you have will have always vectorial components on the algebra, on the basis of the Clifford algebra. And of course, is not an inner product in standard way. It's only an inner product if you restrict, if you take only its scalar part. Nevertheless, if you want to construct functionals and use the Riesz representation theorem, it's exactly this call it pseudo in a product that you will be needing. Actually, if you also want to study positiveness of matrices, for instance, you need to enter to this condition, but the determinant of this matrix have to be considered with this inner product that you, well, pseudo inner product that you have here. But that is not the only difference that you have because of the lack of non-commutativity. For instance, the quaternions are the last of the algebras where the norm of the product is still the product of the norms. You can have the same thing on octonions, but then the situation becomes much harder because you not even lose commutativity, you also lose associativity. And since you want to study compactness of the operators, you want to study also eigenvalue problems. And the eigenvalue problems, it's quite clear when you have matrices of real valued or complex valued operators, which you simply demand that this operator is not invertible to calculate the spectrum. But if you have a Clifford value operator, what possibilities do you have? First of all, you want to apply the operators on the left, which means that if your candidate to eigenvalue, it's also on the left, you have right linearity, everything goes perfect, but in the moment you try to decompose, apply again another operator, ds is on the way. You have a lot of papers discussing this type of right eigenvalues for Clifford value operators, but in fact, they only make sense if your eigenvalue is real or complex. The eigenvalues that one is interested, ones that allow you to construct something, is when the eigenvalue is calculated on the right of the function. Then you can decompose the space of the functions and you can apply the operators to this and obtain decomposition. The problem is this is a non-linear operator and it has more problems. For instance, this, in the moment you have one such eigenvalue, what you do have is not an eigenvalue, but a representative of class of equivalence classes of eigenvalues. Is enough that you multiply by a unit element here, you rotate your eigenvalue, and all of these satisfy exactly the same element. So based on an idea on Sabadini and Colombo, there was a construction of spectrum, S spectrum, based on the Poisson kernel for the quaternionic case, since they observed that multiplying this element, which is linked to the Poisson kernel, by this series here, which is an easy to control series, give you simply T minus S par. So you can use this operator, which is a second order operator, T square, as a counterpart of the resolvent operator in the classic sense. But of course, since this is of second order, you have to multiply it by T minus S bar in order to get correct order. So the spectrum associated to an operator is simply the set of elements, and this is obvious an error, which this is not invertible. So you have the pseudo-resolvent operator and DS resolvent. So the elements in which this is invertible is simply the quaternion minus the spectrum. So with this, then one can indeed define the operators with pseudo-differential symbols taking values in Clifford algebras with quaternion values. As you can see, the character on the inverse Fourier transform is a complex one. So most of the proofs go straight forward, but not all. And you have the definition of the symbol demanding exactly smoothness and evaluating the derivatives in the torus with the discrete Dirac operator, powers of that, in terms of the decay in the lattice. Now, the consequences, some of the proofs go strictly forward directly. For instance, the convolutional kernel representation has nothing of difference. But interesting is to try to obtain a condition of ellipticity. We say that the symbol defined an operator elliptic of order m if its symbol satisfies this condition that you have here when the lattice is large enough. So for values of the m of the lattice larger than m. But if you look at this, then you have an obvious consequence that the discrete star Laplacian, while the continuous one is an elliptic operator, the discrete star Laplacian can no longer be a discrete elliptic operator, since there is no way you can control it. It can be larger than this. You can make it as small as you like. So the boundness of an operator, you simply consider that the boundness of the operator simply impose that the derivatives in the frequency domain are bounded, and this construct a relatively nice space. So the only problem is that when you go for an operator taking values of quaternion, then the essential spectrum has to be replaced by the notion that this, the inverse of the Poisson kernel, has to be a Fredel and have index 0. If this is, then you can have the compactness if and only if the D, this limit of the supreme, is 0. So now I have a problem. So let's view the classic continuous case of the class. For the Laplace operator, you have the different classes here, indicating that the degree of decay of the Laplace operator of the Dirac, so decrease regularity, decrease 1, the Theodorescu an integral operator, so the decay increase, and the Hilbert, the regularity increase, and the Hilbert transform, which change nothing in the operator. If you pass for the discrete case, then you observe that all of them are going to be exactly in the same class, which actually confirm the fact that we know that the discretization introduced some kind of regularization process. So the star, in conclusion, the star Laplacian and the discrete are bounded operators in the discrete setting in lattice. None of these are satisfy the compactness condition, and the discrete allows this kind of theory allows you to study discrete Riemann problems with non-constant coefficients. So these are some some references. These referring to the cases which were already defined by Rabinovich to take care of discrete operators in terms of pen-denominated operators. In the second article, we were taking into account the notion of S-spectrum regarding normal quaternionic operators. These two were developing the study and applications for the discrete Hardy spaces and boundary value problems. And the last one was the paper that gave the idea of constructing these pseudo-differential cases for discrete operators. So maybe I have been too fast, but I'm quite sure that everybody enjoyed that.
Okay, thank you very much for this talk. So are there any questions?
Maybe I ask Paula, this can you, maybe I missed, I'm sure I missed it, but when you make this splitting of EJ into EJ plus and EJ minus, how do you choose them?
Just a moment, because you didn't miss it. It was one of the points where I didn't indicate there, although I'm trying desperately to go to the slide. The fact is, you in fact, you have your EJ and you decompose, you plunge that element in a complex plane. You pick its orthogonal complement in an algebra such that the square of this new element is plus, so it replicates the complex case, and now you make the middle of the sum or of the difference. And that's how you construct these elements, which now satisfy these nice conditions.
And also that EJ is the sum of these two. This is
yes,
a consequence of this construction.
Yes.
Okay. Okay, thank you.
Questions?
I just have a simple question. Usually when you define the Dirac operator, the symbol is wedging with psi and contraction plus contraction with psi. So in your case, the symbol had only one component. Could you explain this? I'm not familiar with the calculus, so maybe there's a simple reason.
Contraction with, sorry, can you repeat?
If you look at the Dirac operator on Rn, then usually the symbol is given by, or say simply D, right? Then the symbol is given by contraction with psi on forms, right?
Yes.
And wedging with psi. So it's a sum of two.
Yes, but in this case, when we work on the Dirac operator that we are using is simply the vectorial part. You have simply the sum of the derivatives EJ. There is a second operator, which is the gamma operator, which gives the rotational part of this, which I believe that correspond to the wedge part that you seem to be missing in this case. But the problem is when you have the Dirac, so the vectorial part, you can obtain the rotational, the angular part of the operator simply by making wedge with the element, with the X element. So you only need this vectorial Dirac operator to obtain all the components.
Thanks.